is reduced by a protein that's called flavodoxin. And flavodoxin is a protein that has a cofactor, which is a flavin, and that's also a vitamin B, as it turns out. They're both vitamin Bs. So vitamin B12 has a redox potential or a standard reduction potential of minus 0.526 volts. And that is very low number for a biological system. And flavodoxin has a potential of minus 0.23 volts. So which of these things is a better reducing agent? So which thing, you want to think about reducing agent, which thing would prefer to be oxidized and reduce something else? So with the low negative number, B12 is a better reducing agent than flavodoxin. And just based on these numbers, vitamin B12 should be reducing flavodoxin, not the other way around. So how does this work then? So in this, in your body, right now, you have a version of a flavodoxin protein, and you have vitamin B12 attached to an enzyme, methionine synthase. And for that to be activated, it needs to be reduced. So how is this happening? So let's consider whether the reduction of B12 by flavodoxin is spontaneous. It happens in your body, so one might think that it is. But let's look at that. So we can look at it the same way you've looked at all the other systems. We're talking about batteries, electrochemical cells. You can use the same equations if it's a biological system as you can for any other system. So we've seen this equation before. We've calculated changes in the standard reduction potential for a cell. And we talked about the E naught for reduction minus the E naught for oxidation. And we can use that same equation. So we can put it in the biological context. The vitamin B12 is the thing that's being reduced, and the flavodoxin is the thing that's being oxidized. That's the reaction that happens. So we can plug those values in. So we have minus 0.526 volts minus a negative 0.23 volts. And if you put those together, you get minus 0.296 volts. So is that going to be a spontaneous reaction? No, it's not going to be. Your value for the E is negative, which means what is true about delta G? Positive, so it won't be spontaneous. So let's figure out how not spontaneous it's going to be. How much trouble are we all in? So we can use, again, the same equation that we use for batteries that we've used in this course. Just because it's a biological system doesn't mean the equation doesn't hold. So our equation for delta G naught minus n, the number of moles of electrons, times Faraday's constant, times the change in the standard potential. So we can plug it in. I can tell you it's a one-electron process. Flavodoxin puts one electron into vitamin B12. So we have minus 1 times Faraday's constant times the cell potential difference you just measured, which is minus 0.296. And if you multiply those out, then you get 28.6 kilojoules per mole positive. That is a very big value. That's not spontaneous, and it's not a small number for a biological system. So why don't we all have heart disease and megaloblastic anemia? Those are problems associated when this particular enzyme is not functioning. So what happens in this system is what happens in a number of biological systems. How do you drive something forward that is not spontaneous? And what you can do is put energy into the system to drive that non-spontaneous reaction. And in this case, the energy that's put into the system is from a molecule called S-adenosylmethionine. And the cleavage of S-adenosylmethionine has a delta G naught of negative 37.6 kilojoules per mole. So it's more favorable than the reduction of B12 is unfavorable. And so this drives the system. So S-adenosylmethionine